Hello and thank you for watching my video. My name is Astrit Krasniqi. I'm CCNA and CCNP certified instructor. On this video we are covering interconnecting Cisco networking devices part 1 or ICND1. This is for exam 100-105. Now we're moving on to section 1.6. Select the appropriate cable type based on implementation requirements. Connecting to the network. Whether connecting to a local printer in the home or to the website in another country, before any network communication can occur, a physical connection to a local network must be established first. So you have to have a physical connection to be able to connect anywhere, whether it's local or remote. Many homes, for example, individuals are implementing home integrated service routers, ISRs. Now, what are these routers? For example, if you look, they will have a console port here to manage. And they will have for example, 4 ports here as a switch. Then you will have the internet ports or routing ports. So this is like a switch on this side and it becomes a router on this side. So some of the routers here, they will have wireless as well. Yeah. So they will be like an access point. That's an integrated router. As well as, for example, this will be a firewall as well. Firewall. So this router is doing many jobs. It's doing access points, switching, routing, and firewall. That is called integrated service router. So ISRs offers a switching component with multiple ports, allowing multiple devices to be connected to local area network, LAN using cables. Additionally, many ISRs also include a wireless access point, which allows wireless devices to connect as well. Network interface cards. Network interface cards, or NICs for short, connects the device to the network. We have a wired NIC and wireless NIC. So if you connect to with the wire, you would have the network interface card looking like that. And wireless, it would look like that. They definitely they will look differently on the laptop. For example, they will be integrated, and obviously the Ethernet as well. NIC will be integrated on the motherboard as well. A wireless device will experience degradation in performance based on the distance from the wireless access points. You know, the further you are, you're going to lose the signal. Your signal is going to get bad. You're going to maybe even drop the signal. So closer you are, you're going to have a better performance. For example, what you could do is you could implement something called a wireless LAN with a range extender. What these devices are, for example, imagine if you are, this is your home, yeah? So, or a home where you're connecting. So it has maybe 3 floors. So you have the router here is going to give the wireless access, but that wireless access is reaching only the 2nd floor, but not the 3rd floor. What you could do, you could implement these range extenders. They come in at like 2 devices. They communicate with each other. So you put this device here in the plug, in electricity on your home, and then that's going to be using the electricity around your home and communicate with the other wireless extender on this side, on the 3rd floor. And that's going to extend your wireless accessibility or wireless reach here. So that's the good thing. A wireless extender, range extenders. I have one. I use one. Not that my house is 3rd floor, but hey, it still loses the signal even in the 2nd floor. Alternatively, a wired connection will not degrade in performance. However, it's extremely limited to movement and generally requires a static positioning. Network interface cards, or NICs, there are 3 basic forms of network media. The physical layer produces a representation and grouping of bits for each type of media, as we have a copper cable that we are familiar. That's usually our UTP, Unshielded Twisted-Pair, which you're going to see very soon. The signals are patterns of electrical pulses. Fiber-optic cable, the signals are patterns of lights. And then we have a wireless. The signals are patterns of microwave transmissions. So we have 3 types of media: cable, copper cable, fiber cable, and wireless. These are the characteristics of copper media. Transmitted on copper cable as electrical pulses, as we said. Attenuation: the longer the signal travels, the more it deteriorates. All copper media must follow strict distance limitations. Electromagnetic interference, EMI, or radio frequency interference, RFI, distorts and corrupts the data signals being carried by copper media. For example, if you look here on the right, we have a pure digital signal here. And then we have the interference, and that's the signal with interference. As you can see on this bit here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9th bit. 9th bit, the interference was quite high, and that 0 became 1. So obviously this data is corrupted. To counter this interference, a copper cable is wrapped in the shielding, which we're going to see very soon. Crosstalk, this is disturbance because of the electrical or magnetic fields of a signal on one wire to the signal in adjacent wire. So this is like wires inside the cable, they do crosstalk with each other. So one has some kind of interference or disturbance with the other wire. To cancel crosstalk opposing circuits, wires pair twisted together. So there are three main types of copper media used in the networking. We have unshielded twisted pair. These are very good, very easy, very flexible, and the most that we're used to anyway. But if you do have some kind of interference, radio frequency interference or electromagnetic interference, then we use a shielded twisted pair. These are a bit more expensive, but they have a shield. Some even more expensive, they will have a shield. Each pair will be shielded as well. One of the old cables that we had is Coaxial. They are not that much used anymore, but if you have a satellite TV, most likely there will be a Coaxial cable at the back of it. These cables are used to interconnect nodes or end devices on a LAN and infrastructure devices such as switches, routers, and wireless access points. An unshielded twisted pair cable is a 4-pair wire, so there's 8 individual copper wires. They are covered in insulating materials. In addition, the wire in each pair are twisted around each other. The advantage of unshielded twisted pair cable, it is the ability to cancel interference because the twisted wire pair limits the signal degradation from EMI and RFI. The more the twist, better protection from interference. Less twist, worse protection. It will actually say there in the cable. If you look at the cable, that will tell you how much is the twist. Unshielded twisted pair connectors. Now we use the unshielded twisted pair cable does connect with an RJ45 connector, or does terminate with RJ45 connectors. The TIA EIA 568 standard describes the wire color codes to pin assignments pin out for Ethernet cables, which you're going to see at the next slide. It is this standard. RJ45 is the male component crimped at the end of the cable. Socket is the female component of network device, wall, cubicle partition outlet, or patch panel. It is essential that all copper media terminations be of high quality to ensure optimum performance with current and future network technologies. So for example, when you terminate, you have to make sure that this shielding is inside the connector as well. The types of unshielded twisted pair cable, the following are the main cable types that are obtained by using specific wiring conventions. So we have an Ethernet straight through cable, the most common type of networking cable, and it is commonly used to interconnect host to a switch and a switch to a router. Now this standard, for example, TIA 568B says it's like a color coded for us what we need to put. It says on pin 1 we need to put white and orange. Pin 2, orange. Pin 3 has to be white and green. Pin 4 and 5 is blue and white blue. Pin 6 is green. 7 and 8 is white, brown, and brown. Now pin 4, 5, 7, and 8, they are idle. In 100 megabits per second, they don't get used. So we only use pin 1, 2, 3, and 6. Same on the other side. Now if we put exactly the same on both sides, that's going to give us a straight through cable. If we use 568B in one side, like similar to what we had here, and TIA 568A in the other side, that will make a crossover cable. Now crossover cable is not used that much, but only when we connect similar devices together. So this similar device, router, is different device to the switch, so we need a straight through cable. Router to another router, then we need the crossover cable. This says pin 1 and 3 are going to be flipped. For example, pin 1, for example, here it was white and orange, here becomes white and green. Pin 2 is orange. Pin 2 here becomes green. Pin 3 used to be white and green on this side, and it's white and orange on this side. And then pin 6 as well. It's orange from green. And then the third type of cable that we have is called rollover cable. Now, rollover cable is a Cisco proprietary cable. This is used to connect a workstation to a router or switch console port. If you want to do, like, for example, start up the management of the device, you plug into the console cable to console port. Now, if I go back a bit early here, like for example, if you want to connect this, if you want to manage this device, you will connect to the console port here, and you need a rollover cable. In the rollover cable, for example, what we have is a pin 1 connects with pin 8, pin 2 with pin 7, 3 with 6, 4 with 5, 5 with 4, 6 with 3, 7 with 2, and 8 with 1. It's a rollover cable. When to use a straight through and when to use a crossover cable. So for example, if we connect a switch to a switch, that's a crossover cable. If we connect switch to hub, switch and hub, similar device. So it's a crossover cable. Hub to hub is a crossover cable. A router to router, we will use it as a crossover cable. Router to PC, that's a crossover cable. Because the router is just an advanced PC. It's actually a PC, advanced PC. If we connect PC to PC, another crossover cable. So here, for example, there's a feature called auto in the switches, yeah, in the newer switches, auto MDIX. Now, auto MDIX, what it is going to find out what cable there is. So even if you put a straight through cable, auto MDIX is going to fix the pins for you. So it's kind of like finds out what's the other side, what sort of device is it. If it's a switch, it's going to fix the cable. So even if you connect a straight through cable, it will work. But auto MDIX is only available if you have the speed, and if you have a duplex set to auto. That's the requirement for auto MDIX to work. If we have a straight through cable, straight through unshielded twisted pair, this is most common. We can have a switch to router, that's going to have a straight through cable. Switch to PC, a straight through cable. Switch to servers, yep, straight through cable. Hub, well, hub is same as the switch. So if we connect to the PC or to the server or to the router in that case, we will still have a straight through cable. Ethernet LAN connection media. The most common LAN media is Ethernet. Ethernet is a standard that IEEE has published. So there is various Ethernet terms such as Ethernet protocols, Ethernet cables, Ethernet ports, and Ethernet switches. So for example, sometimes we see 10 base T. Now that says what's the speed, and is it baseband or broadband, and what's the cabling. So prefix, for example, speed in megabits per second. We could have 10 megabits per second, 100 fast Ethernet, 1000, which is gigabit Ethernet, or we could even have a 10,000, which is 10 gig Ethernet. Baseband or broadband, so the baseband says one data stream, only Ethernet, or broadband you could have more than one stream. T is the suffix. It's just kind of like it tells you what is a cable type and the maximum distance. So for example, if you have a number 2 there, or 5, that means it's a coaxial, and the distance is 200 meters for 2, and 5 is for 500 meters. Letter T means it's twisted pair, and the maximum distance is 100 meters. If it's E, that says for single mode fiber, 40 kilometers, or F, that's a multimode fiber, 2000 or 2 kilometers. S for multimode fiber, 300 meters. So requirements, media, maximum segment length, and connectors. So 100 base T, 100 megabits per second. Baseband, it uses TIA category 5, 2 pairs only. And the maximum segment is 100 meters. The connector, RJ45. 100 base FX, this is a multimode fiber, 400 meters. Duplex make MIC and ST, straight tip, the connectors. 1000 base T, that says, okay, well, we're using a gigabit, or 1000 megabits per second. Using a 5E category cable, which is unshielded twisted pair, but we're using 4 pairs. 1000 meters and RJ45. So in 100 base T, we're using only 2 pairs, which means four pins. 1, 2, like I said, 1, 2, 3, and 6. Here we are using all the pins in 1000 base T. 1000 base SX is like a fiber, multi-mode fiber, and 1000 base LX is a single mode fiber. So properties of fiber optic cabling. Fiber optic cabling transmits data over longer distances than the copper cable and at higher bandwidth. Transmits signals with less attenuation and is completely immune to EMI and RFI. Flexible but extremely thin. Transparent strands of very pure glass, not much bigger than a human hair. So I don't know if you've seen a fiber optic, but they are very, very thin. Not much on the bits are encoded on the fiber as a light pulses. So this is what's inside the fiber optic cable. So we have a protects the jacket, which protects the fiber against moisture and other contaminants. Composition can vary depending on the cable usage. Strengthened material surrounds the buffer. Surrounds the buffer, prevents the fiber optic cabling from being stretched when it's being pulled. And this is the same material that we used as in the bulletproof vests. The buffer then we use to help shield the core and the cladding. And then we have two glasses here. First is cladding, which is a bit cheaper glass, but tends to act like a mirror by reflecting light back in the core of the fiber. So if the light is trying to escape, the cladding will put it back. And then we have a core, which is a pure glass, very expensive, and in here we transmit the fiber optic cable. We transmit the light. So light pulses travels through the fiber core. So light pulses are represented, the transmitted data is a bits on the media and generated by either laser or light emitting diodes, LEDs. So the laser light transmit over fiber optic cable can damage the human eye. So you have to make sure that you don't actually look at the fiber optic cable if it's connected on the other side, because it can blind you. So fiber optic cables are broadly classified into two types. We have a single mode fiber. This consists of very small core and uses expensive laser technology to send a single ray of light. It's popular in long distance situations spanning hundreds of kilometers. The core is 9 microns and the cladding is 125 microns. So you can see that's a core, 9 microns, and 125 is the cladding. Then we have a multi-mode fiber, and there's two variants on this. And they transmit not a laser, but they do transmit LED, so light emitting diodes. And then they can transmit up to 10 gigabit per second in the length of to 550 meters. So there's two types in multi-mode. So we have one with a 50 microns core or 62 microns core, and the cladding is 125 microns in the diameter. Fiber optic connectors. Light can only travel in one direction over optical fiber. Two fibers are required to support the full duplex operations. Well, there's new technology around there. They come up that actually you can have one strand of fiber that can send both ways. But anyway, that's new. So straight tip connectors, one of the first connector types, is used to lock securely with twist on and twist off. And subscriber connector, these connectors referred to as a square or standard connectors. Used to push-pull mechanism to ensure positive insertion. Used with multi-mode and single mode fibers. Loose end connectors, simplex connectors, smaller version of SC or smaller version of subscriber connector and popular due to the size. And duplex multimode LC connectors, similar to LC but used in duplex connectors. Now wireless media. Now as we see these signs anywhere, if we go around and we see this sign, we know there's wireless availability there. Now when you use wireless, we have some concerns. One of the main concerns is coverage area. How far can you go with a wireless device? Wireless data communication technologies works well in open environments. So if you have in the field, nothing in there in front of you and the access point, great, you can go to further distances. But if you have a buildings in your structures and local terrain, that will limit the effective coverage. The second concern, what do you think it is? Okay, the second concern will be the interference. Wireless is susceptible to interference and can be disrupted by such common devices as household cordless phones, some types of fluorescent lights. Microwave ovens are the worst one for the interference, and other wireless communications as well. Then one of the main concerns that should be in the wireless is security. Anyone within the range can access our wireless network. So we have to make sure that we have some kind of like a security implemented. So network security is a major component of wireless network administrations. And the wireless network works in the shared medium. So WLAN operates in a half duplex, which means that only one device can send or receive at a time. They work in the protocol, like early on we were talking about the hub. It works in carrier sense, multiple access, but this is not detection. This is only going to have collision avoidance. So in this protocol, the wireless devices work. Types of wireless media. So we have a Wi-Fi, we have a Bluetooth, and WiMAX. These are some of the standards that you really need to remember for wireless. So IEEE 802.11, that's a main standard for Wi-Fi. So commonly it's referred to as Wi-Fi, and again it works in the carrier sense, multiple access, collision avoidance. Some of the variations we're going to see very soon in this next slide. These are the standards that have been released. The Bluetooth is 802.15 standard, and you have to remember that very well. Supports speeds up to 3 megabits per second. This provides the device pairing over distances from 1 to 100 meters. I don't know. I never had a Bluetooth that could connect to 100 meters. Anyway, there's a Bluetooth like short range, medium range, and long range, but 100 meters, not sure. Anyway, that's what he says. That's all you have to remember. 802.16 is the WiMAX. This provides speeds up to 1 gigabit per second. It uses a point-to-multipoint topology and provides wireless broadband access. This is like a 4G. You use mobile towers and stuff, but it's not 4G and 3G and 5G and whatever. This is the WiMAX. So a wireless LAN, a common wireless data implementation, is enabling devices to wirelessly connect to LAN. In general, a wireless LAN requires the following network devices. Wireless access point. This concentrates the wireless signal from users and connects usually through a copper cable to an existing copper-based network infrastructure such as Ethernet. Home and small businesses wireless routers integrate the function of a router, switch, and access point into one device, as you can see it on the figure. This is integrated router, yeah? And then we have a wireless NIC adapters. These provides wireless communication capabilities to each network host. Some of the Wi-Fi standards, 802.11. So A and B came out at a similar time. A came out first, maximum speed 54 megabits per second, but the frequency works at 5 gigahertz. Backward compatible? No, because there's nothing to be backward compatible with. 802.11b, it's 11 megabits per second, but this works in frequency 2.4 gigahertz. Now 5 gigahertz is worse than 2.4 because 5 cannot penetrate as easy through walls and stuff better than 2.4, and you will lose that speed. Further you go, longer distances, and the maximum speed drops very, very quickly. While B, the speed will maintain there. Then we had the 802.11g standard that came out, so they kind of like equal to the speed of 11a, which works in same frequency as 2.4. This is backward compatible with 802.11b. Then we have 802.11n. This is maximum speed now, which has increased to 600 megabits per second and can use both frequencies, 2.4 and 5 gigahertz. Now the thing is about this, we have to remember that from the standard N, we have something called MIMO. Multiple input, multiple output. You know, when you have the devices, the APs, they have two antennas. Until then, they had only one antenna. From the standard N, they can use more than two antennas, two or more antennas. Then we have the 802.11ac. There you can see the speed has increased, and both frequencies and the backward compatible with B, G, and N. And 802.11ad, 7 gigabits per second, And this is works at 2.4 GHz, 5 GHz, and 60 GHz. And it's pretty much backward compatible with B, G, N, and AC. So comparing WLAN, or wireless local area network, to a local area network. Now WLAN is going to need a radio frequency, while 802.3, that's Ethernet, is going to need a cable. Media access, this is collision avoidance, while Ethernet LAN is collision detection. Availability, anyone with a radio NIC in range of an access point has got availability for wireless. For Ethernet cable connection, it is required. Single interference, yes, we have it on wireless. No, we don't have it on Ethernet. Regulation, additional regulation by country authorities. Now, the frequencies 2.4 and 5 GHz are free to use, not in every country, but in most of the countries around the world. So here 802.3 regulation is IEEE standard dictates. Thank you for watching this section. 1.6, select the appropriate cabling type based on implementation requirements. Please have a look at my other videos and don't forget to subscribe. This has been Astrit Krasniqi. Bye bye.